welcome back to Introduction to Photonics. We have been talking about semiconductor light detectors, and specifically we talked about avalanche photodiodes. So, in the last lecture we were talking about gain for an avalanche photodiode. So, the gain is denoted by this multiplication factor m, which we say is the total electron current density after the multiplication region divided by the current density that you had before the electrons entered the multiplication region. So, we said we could go through some rate equation, and we could solve it and finally get to an expression that is given like this in the bottom right portion of your screen, where m is given in terms of alpha e and alpha h. So, you can actually define at this point a quantity known as the ionization ratio. Let us call that k, such that this is given by alpha h over alpha e. Okay. So, what does that mean? It is a ratio of the impact ionization coefficient for holes divided by impact ionization coefficient for electrons. So, for materials like silicon and gallium, in indium gallium arsenide, what can you say about value of k? Is k much less than 1, k equal to 1, or k much greater than 1? Huh? K is much less than 1 because alpha h is lesser than alpha e. Just to give you an idea, k can be greater than 1 in certain material, like indium phosphide is a very good example, where in indium phosphide the impact ionization coefficient for holes is greater than impact ionization coefficient for electrons. So, k can be greater than 1, but for indium gallium arsenide we have k being approximately equal to 0.5. Of course, it can change based on the material that you are using and also the specific configuration that you are using for your avalanche photodiode. But in silicon, k is about 0.1, right, and once again by designing things appropriately, k can even be less than 0.1 for silicon. 0.006 has been demonstrated. Okay. So, now if you define this, then what you can do is, in this expression for m, both in the numerator and the denominator, you can divide by alpha e. Okay. Then you can get an expression in terms of k. So, let's do that. If we do that, what you get is m will be equal to 1 minus k divided by exponential of minus of 1 minus k alpha e w m minus k, right. I have just all I have done is I have divided both the numerator and denominator by alpha e. So, you get 1 minus k over here, and you get factor of 1 here, and within this also you have 1 minus k and alpha e goes out, right, and then in the last factor is k. Okay. So, that is what we have written here. So, if I plot this for different values of k, okay, I can plot m for different values of k, m as a function of alpha e w m. So, let us do that. let us look at m as a function of alpha E W m. Now, W m is a constant. Once you have your design for your avalanche photodiode, W m you are not going to be able to vary. Can you vary alpha E? Alpha E corresponds to the impact ionization coefficient. What does that depend on? The electric field, right? The electric field existing in that region, and that electric field is dependent on the applied voltage, reverse bias voltage. So, as I increase my reverse bias voltage, I can increase alpha E. So, I can as well plot this as a function of my bias voltage also, right. So, if I plot this function, what do I get? Now, where for k equal to 0, right, my impact ionization coefficient for electrons is far greater than alpha h. If I have that case, then k is can be approximately 0. If k is 0, then you get m equal to 1 over exponential of minus alpha E W m. Right, which you can write as, so m equals to exponential of alpha E W m, right. So, how does that look over here? So, that I am going through an exponential here. This is for k equal to 0, you are starting from m equal to 1, right. So, it is just an exponential dependence. Now, the other extreme is for k equal to 1, right. For k equal to 1, which means that impact ionization coefficient is the same for both electrons and holes. Okay. In that case, what do you get? 1 minus 1 0. So, and the denominator is also 0. So, 0 by 0. So, indeterminate solution. So, you go for L'Hospital's rule, right. You take a derivative of the numerator and the denominator, and you look at that. And if you do that, what you will get is m equals to 1 over 1 minus alpha E W m is what you get. Okay. Sorry. So, how do you plot that? Here let us say this is 1, 2, 3 and so on. So, this is asymptotic with respect to alpha E W m equal to 1. So, in this case it will be something like this. Okay. So, question is, what do you prefer? Do you prefer k equal to 1 or k equal to 0? So, k equal to 1 says even at very low voltages I can get very high levels of gain. So, you would normally say, yeah, that is preferable, right. I do not have to go very high voltage to get my gain, and I mean you will not be completely wrong with that, except that you think about it, k equal to 1. So, both your electrons as well as your holes are equally capable of generating this avalanche. Okay. Electrons will keep drifting this way and creating havoc, creating this avalanche in this direction. Holes is actually drifting this way, and that is also creating a lot of secondary electron hole pairs. That is also creating avalanche. But the problem is, every time we talk about creating an avalanche, we are talking about a statistical process. it is not like one electron is going to go hit this atom and then that is going to hit another atom and that is going to hit another atom. So, for one electron m equal to 10, it is not always m equal to 10. M now is varying, it's sort of random, right. So, m can be 7, n can be 20 also in some extreme case, very low level of probability, but in principle it can be whatever value, right. So, it actually generates noise, okay, in the multiplication. But anything that is random, you can say that is going to be noisy process, right. So, even when you do it with an electron, it is already noisy. Now, if you do it with holes, it becomes even more noisier, because those are two different independent processes in terms of creating that avalanche. Okay. So, you have much more noise, much more chaos essentially happening when you have both of your carriers generating avalanche independently. You have a question? Yeah. That's right. So, yes. So, physically question is no, holes are we say spaces occupied by left behind by electrons, but in a highly charged electric field, if you have a hole, it is going to be replaced by another electron, right. So, you are going to have these holes filled by another electron, and in that process you essentially have the holes moving this way. So, although physically you cannot think of this hole generating an avalanche process by itself, the hole does create a perturbation which essentially generates secondary electrons that are left behind, right. So, with this high electric field, essentially what we are saying is that hole propagates. How does the hole propagate? Because the neighboring electron will occupy this hole. So, the hole will go this way, and then that neighboring electron from there it's going to come here, and so it's as if the hole is propagating. But in that process, in the process of electron jumping over, it can actually ionize, and so you say holes are generating avalanche as well. So that's a very good question, but whenever there is a hole, there is also transport of an electron that's happening. So that's actually as if the hole is going that way. Okay. So you don't want k equal to 1 from that perspective, because that essentially means, if I go back and look at this discussion we had in this impact ionization, the dotted and the solid lines are overlapping each other. So, for the same electric field, both of them happen, right. Both of them have the same threshold. So, both of them happen, and that creates more uncertainty overall in your secondary electron hole pair generation. So, that would be an issue here. Okay. And to put things in perspective, if you are talking about silicon has k equal to 0.1. So, that will be somewhere over here, and for indium gallium arsenide, k equals to 0.5. So, that would be something like this. Okay. So, yes, indium gallium arsenide you can say has got higher impact ionization coefficient. So, even for low voltages it gives you much gain, but beyond a certain point you start triggering your holes also to provide the avalanche multiplication. So, that can become very noisy. So, In other words, you cannot appreciate this picture without seeing the corresponding noise picture, right. So, that noise picture is represented by what is called an excess noise factor, right. So, we need to consider this excess noise factor, which we can represent as F. Okay. Why do we call it excess noise factor? That is to say that inherently in the photodiode you are going to have some noise. Okay. We will come back and look at what is the basis of that in a few minutes, but beyond that noise process you may have extra noise because of this avalanche process. That is why it is called as a excess noise factor. Now, the excess noise factor, I do not have a derivation for this, because the derivation is actually a very long derivation. I can give you a appropriate reference if you are interested in, but this excess noise factor is given by this expression F equal to K m plus 1 minus K multiplied by 2 minus 1 over m. Okay. So, if you plot this, I will plot f as a function of m, which is actually a function of the bias voltage. So, you can also say that f is being plotted as a function of the bias voltage. So, you have one case where k equals to 1. If you put k equal to 1 in this expression, the second factor goes away. So, you are just having a straight line k equal to 1, right. Whereas, if you look at k equal to 0, right, if k equal to 0, the first factor goes away, the second factor becomes 2 minus 1 over m, and that is just something that is asymptotic with a value of 2 over here. So, it will go somewhere like this. This is for k equal to 0. So, which one would you prefer now? Here then you are getting gain, but you are also accumulating noise, right, as rapidly as you get gain. So, overall you are not improving a signal to noise ratio, right. Whereas, in the other case, when k equal to 0, it essentially gets it levels off beyond initial values of m. So, beyond certain value of m, all you have is gain and not so much of loss, because you do incur extra noise just because the electron is going to create that variability in terms of achieving gain. The gain is not a fixed value, but you do not get any more noise because of holes kicking in. And in between, if we look at for silicon, it will be something like, I am sorry, I do not think I am following the same colors as the other graph, but for silicon it will be something like this. At low values of m, the second factor dominates. For large values of m, the first factor dominates, right. So, this is for k equal to 0.1, and for indium gallium arsenide, is something like this, k equal to 0.5. So, and just to give you a perspective, let me cut and paste this also. let's see. Okay. Right. Like I said, I am not using the same colors for both the thing, but bear with me on that. But you get the idea that it is not just the gain as an absolute number that you get, is the quality of gain that you get, right. So, the quality of gain is defined by how much noise are you accumulating with respect to the gain, and from that perspective there are some interesting observations you can do. You can, if you had indium gallium arsenide and if you were to choose the best gain at which you can get the maximum signal to noise ratio, where would that point be? We are looking at that blue curve on the right graph, right, and we are trying to figure out where would I want to operate, right. I would want to operate somewhere over here, the knee point, because until that point I have not accumulated a whole lot of noise, I have fairly good gain, but beyond that point if I am trying to achieve more gain, I am also accumulating noise, right. So, that would be my operating point for indium gallium arsenide, and for silicon somewhere over there, right. So, those will be my these will be my optimum operating point, right. So, it tells you that of course, as you keep increasing your bias voltage, at some point you are going to get into breakdown, right. We talked about the IV characteristics, right, somewhere over there. I am trying to figure out where it was that we discussed that. So, we talked about IV characteristics and we said beyond a certain voltage it is going to punch through, it is going to break down, right. So, you will have a similar breakdown voltage limiting this. So, beyond a certain voltage you are not going to be able to get any more gain because the device has punched through. But what this picture is showing, you should not even wait until then, until that breakdown voltage. There is a optimum point before that where the signal to noise ratio you are not getting any improvement. Okay. So, you need to stop at that point. Okay. And we will look into this a little more detail as we start discussing about noise, but I just wanted to give you that picture, right. And it also tells you that the amount of gain that you can extract from your indium gallium arsenide, the optimum gain is going to be lesser than that you extract from silicon, just because of the fact that indium gallium arsenide has a larger k value closer to 1 than what you have for silicon. Okay. So, that is just a material property by itself. Do you understand that? Okay. So, let us actually throw some numbers into the picture. So, what we are talking about here is for indium gallium arsenide, I'll just go to the next slide and talk about that. For indium gallium arsenide, what you will have is you can get the optimum gain to be in the order of 10 to 20, right, before your noise starts picking up. But that you can get with VB, the bias voltage, in the order of 10 to 50 volts itself, because of the fact that your impact ionization coefficient for indium gallium arsenide is higher than it is for silicon. So, if you look at silicon, that M opt can be in the order of 100 to 300 even in certain case. For k equal to 0.006, as somebody has demonstrated, M opt can be even up to 300, and VB also has to be in that level. It is typically 100 to 500 volts is the operating voltage to get that gain. But yeah, you are able to finally get a much higher gain with your silicon than you can with your indium gallium arsenide. That is one picture. The other picture is with respect to the multiplication time. Remember, we talked about multiplication time. We said that is actually an excess time that slows down the response of your photodiode. This multiplication time can be, and I am not deriving this because once again it is a fairly long derivation, but it can be approximated as m multiplied by k multiplied by Wm over VDR. Now, Wm over VDR we know that is just corresponding to the transit time across that multiplication region, but we are multiplying with by m because there are m events, and that is also weighted by the impact ionization ratio k. So, if you calculate this for these above values, we know that indium gallium arsenide k equals to 0.5 is what we are taking, and silicon k equal to 0.1, right. If you substitute these values, let us say in this case you do not need a lot of Wm. So, Wm can be as small as 0.1 micron, whereas here the impact ionization coefficient is not as high. So, Wm needs to be more, it has to have a larger multiplication region, and if you do this, what you will find is if you substitute in here, what you find is tau m equals to 5 picoseconds for indium gallium arsenide, whereas it is in the order of 50 picoseconds for silicon. That is understandable because in silicon you have many more multiplicative events, and also you have to transverse a longer distance with respect to your multiplication region, because the impact ionization coefficient is lower. We have to traverse a longer distance across the multiplication region. Okay. So, it is essentially saying that okay, your silicon APDs are going to have lower bandwidth compared to indium gallium arsenide APDs, which is good to know, but it really does not matter because silicon is going to be used for very different applications than indium gallium arsenide. Indium gallium arsenide, you where would you want to use indium gallium arsenide photodiodes? What spectral region does it address? 1.55, the communication. So, for all your communication applications you use indium gallium arsenide, whereas silicon is more for spectroscopy and other free space applications. So there is no direct comparison between the two. Any questions up to this point? You guys understand this picture? Why there is actually an optimum value for gain? Yeah? Okay. So, let us actually chug along and let us look into another important topic, which is noise in photodetectors. Detectors and the corresponding photo receivers. So, when we talk about noise, there are primarily two types of noises associated with photo receivers. One is called photo electron noise. So, what is photo electron noise? You have photons being absorbed in the medium and you are generating electron hole pairs, right. But we actually quantified a parameter called zeta, which was the photoelectron conversion efficiency. So, that says that not every photon is converted to an electron hole pair. It is like only on the average so many photons are converted to electron hole pairs. When we say on the average, in real time, that means there is actually some random process that is happening. So, there is actually you have photons first of all that are arriving in a random fashion, because we talked about all the light sources. Those all the light sources are characterized by a certain randomness. When we talk about some particular level of intensity, we are always talking about a certain mean number of photons coming through. But if you slice it into small enough time slots, maybe in the order of nanoseconds, then you find that the mean number, the actual instantaneous number is actually fluctuating, right. If we say 10 photons is the mean number, within a very small time slice, that number can be anything. It could be on the average it is 10. So, there is a good chance that it will be 10, but there is also a chance it will be like 8, it will be like 7, it will be like 15 and so on. So, what does that tell you? As from a receiver perspective, you have photons that are coming not so uniformly, and then there is actually the photo electron conversion process that doesn't, that also is impacted by that does not happen so uniformly. So, you have this noise which is it's also called short noise that is happening, right. This is primarily because of random arrival of photons and their subsequent conversion to electron hole pairs. Okay. You understand that? So, that is one type of noise. The other type of noise does not really have anything to do with the photodiode itself, but nevertheless when you are trying to extract a current from the photodiode, you have to flow it through an external circuit and convert that current to a voltage, because voltage is what we typically recognize with all our electronics, right. So, in that process you have something called thermal noise, or it is also called Johnson noise that happens. Thermal noise happens when you send a photocurrent through a resistor, for example. That resistor is going to have a particular value, and it says on the average it allows this much current to pass through, or it allows a certain rate of electrons going through, but that rate actually depends on the number of collisions that it has while it is propagating through that, and that is actually a random process by itself. Okay. So, that current, that noise, because of the random propagation of random flow of current through a resistor, is what you call as thermal noise, okay, or Johnson noise. So, there are two different noise sources, and if we quantify this noise, the noise variance which you can say is corresponding to sigma s square. Sigma s corresponds to the RMS noise, sigma s square corresponds to the noise variance, and the noise variance is going to be given by 2 times E times I p multiplied by B. So, E times I p is actually the noise variance across the spectrum, but it's actually like white noise. It's flat, it's distributed flat across the spectrum, but what our receiver captures is only the components under the receiver bandwidth. The receiver bandwidth is what we are denoting as B over here, and it's actually, since it's a two-sided spectrum, that's where the factor of 2 also comes into the picture. So, it's integrated over 2 times B, and so you have 2 times E times the photocurrent multiplied by B. Essentially, it says that it's proportional to the photocurrent. More the photocurrent that you have, which would correspond to more number of photons that's falling on the photodiode, more will be the variance. This is some concept that we were discussing much earlier when we were talking about photon statistics itself. We were saying more number of photons will give you more variance. Remember, we were talking about Poisson statistics for the arrival of photons, and there the Poisson statistics were proportional to the number of photons, that variance was proportional to the number of photons that are falling on that are being collected. So, here we are talking about that corresponding to the photocurrent that we are picking up. Whereas, if you look at the thermal noise component, that is once again white noise, which is corresponding to the thermal energy kBT over the resistance over which that current is passing through. It's a factor of 4 over here, because it's 2 kBT over RL is the noise variance, but it's integrated over 2 times B. Once again, it's a double sided spectrum. So, it's integrated over 2 times B. So, 4 kBT over RL multiplied by the bandwidth of your receiver, that is the thermal noise. What we want to proceed is to quantify this short noise. When this is for an APD, you can write it like this, but for a PIN can write it like this, but for an APD it also depends on the gain of the APD. So, we will go to the expression for the gain of the APD, which will also incorporate that excess noise factor that we talked about, and then we will see, you know, under what conditions do you use an APD, when do you use a PIN, when do you use an APD. Okay. Let's try to figure that out in the next lecture. Okay. Thank you.